Good afternoon, everyone. Today we're going to discuss regression diagnostics. So far, what we have learned in our previous lessons is we have learned how to create a linear regression model given your variables. So we said that there are certain uh, assumptions that have to be met when we craft linear regression models. Okay. We have learned also how to do a stepwise regression in order to determine our final model. So today we're going to revisit the model that we created. Okay. And after we have created the model, it doesn't stop there. We have to go back and review whether the assumptions under classical linear regression model are met or violated. So let's load the packages that we were using. Okay, these are the packages that we were using. So let me just run this. And let's have a quick review of the assumptions of linear regression. I shared with you this one. Okay, Control C. Let's open this. Okay, so this is economic economic theory blog by who made this? The author is not here. Anyway, so the the author wrote something about the assumptions of classical linear regression model or CLRM. Okay. So this post is about a brief introduction about the underlying assumptions of CLRM, classical linear regression model, aka OLS assumptions, ordinary least squares. And this is based on the theorem by Gauss-Markov theorem. Okay, where in the Gauss-Markov theorem, it states there that the values of your parameters beta null and beta 1 are unbiased, okay, and they have the residuals of this that is generated by these parameters have minimum variance among all unbiased linear estimators. What does this mean among all unbiased estimators? We can have several, we can have many candidates for our beta null and beta 1. Okay, and all of them uh, may be unbiased linear estimators. However, there's only one that will have minimum variance. Okay, so among the many possible values of linear estimators that are unbiased, only one of them, this is a unique pair or unique values of BO and B1, etc., that will generate minimum variance. Okay, so this theorem, the Gauss-Markov theorem, tells us that in a regression model, we have discussed this in the past, the expected value of your residuals, this is the average of your residuals, is 0. And the variance, sigma squared, of your residuals is constant, and it's finite. It's less than infinity. Okay, also, another assumption is that your residuals, epsilon sub I and E sub j, are uncorrelated for all I and j. So we said that this is of no consequence actually for cross-sectional data. Kasi yung arrangement ng data natin can be it can be rearranged. But this is more of consequence pag time series kasi. Pag time series kasi yung epsilon sub I natin and epsilon sub j, yung magkasunod for example na residuals, it cannot be rearranged kasi pag time series it follows a logical arrangement. Okay. So yung OLS natin, ordinary least squares results that are founded on Gauss-Markov theorem, we mentioned them to be blue. No? What's blue? Best, they're the best linear unbiased estimator. Okay? Best linear unbiased estimator. So there are assumptions here under the Gauss-Markov theorem. Number one, dapat yung parameters natin linear. Okay? We're not saying here that the variables, the exogenous variables are linear. Kasi pwede yung x, yung independent variable, pwede siyang ano, it can be a power. No? Kunyari, education, pwedeng education squared. Pwede yun. When you say linear parameter, ibig sabihin yan, your betas, so yung equation natin, beta 1 times education, yung beta doon cannot be beta 1 squared. Okay, we already discussed this. Okay? And this one, merong assumption dito, full rank of a matrix. I'll leave you to read this. Kasi this is all about, this has something to do with linear algebra also. Okay? Tapos explanatory variables natin must be exogenous. Ibig sabihin nun, hindi natin predict, hindi natin minomodel yung explanatory variable natin. Ang minomodel natin, ang predict natin yung endogenous variable natin, which is the independent variable. Okay? So, dapat yung mga ano natin, yung x's natin, mga independent variables natin, should be independent of each other. Diyan papasok yung collinearity. Okay, and then fourth assumption is yung independent and distribution of the error terms dapat independent siya. And may sinama dito yung normal distribution of the error terms. Okay? Ito yung least concern natin, which I'm going to discuss in a while. Gauss-Markov assumption number 5 is refers to normally distributed error terms. However, assumption 5 is not, it's not a Gauss-Markov assumption. In that the OLS estimator will still be blue. Okay? Kung na-violate tong normality ng residuals, okay lang yon. Blue pa rin yung ano natin, yung estimates natin. Okay? So you can read more about this here. Tapos yung mga explanation yan, andi dito. So I'll leave to you guys the explanation of this, of the assumptions. So let's go back here to our text. So these are the assumptions class, linearity of the data, linearity of the parameters. Okay. Then this is just a review, so I'll not anymore go through this in detail. Then the homogeneity of the residuals. Okay, dapat yung residuals natin, dapat constant siya. Hindi pa pwedeng nag-i-increase siya. Non-constant. Either a fanning out or a fanning in. All right, and then number 4 natin, yung relationships ng mga independent variables. Dapat hindi siya strongly correlated or multicollinear. Then independence din ng residuals. And then sinali din natin normality ng residuals. All right, so the data that we used before was wage data. So I'm sure you have already run this before. I-run ko na lang to, hindi ko natitingnan yung structure. Okay? And then let's convert already yung mga categorical variables natin. Baka we might meet some problems if we don't do that. Eh dati kasi pag hindi pa convert to factor, hindi natin magagamit siya sa LM function. Pero ngayon pa pwede na, no? Pero just to avoid some potential problems in the other functions. Ang tagal yan, okay. It took quite some time to load. All right, then I'll run this conversion to factors, and then the structure, we can now see that the race, gender, and civil status are now factors. Okay. All right, then to run the regression, okay, we created this object mod, and we're running a linear model on hourly wage regress on all the parameters. Data is equal to wage. Let's just get the summary. And here we see that there are some insignificant predictors, and we said that we will do stepwise so that the significant predictors are removed one at a time. So we have this using OLS step backward P. where we have to identify what's the significant level of significance, so that what's a p-value, so that the variable will remain. Okay. If I run this, it will tell us which variables were deleted or removed. So first race, number of dependents, and experience. So 3 variables removed out of the 7. Okay, so we can now run our model. Our model is linear model, hourly wage regress on the 4 remaining variables. This was our final model last time. Okay, I hope you remember. If I run this, so we now have the new model. It overwrote the mod a while ago. We have now your 4 predictors, and they're all statistically significant. Education, tenure, gender, and civil status. Okay, so this was where we ended last time. Okay, but we said that it's not enough for us just to state that our final model is hourly wage is equal to negative 0.216 plus 0.53 times education plus 0.15 times tenure plus 1.71 times gender minus 0.69 times civil status. That's not enough. We will have to evaluate if our model violates any of the assumptions of the classical linear regression model. Okay, so let's do that. So we said that we can make use of the plot function. Okay. We can use plot for our regression object here, mod. Okay, let's partition the row into 2 by 2. And if we run this, okay, I'm sure you can easily run that. So this is our plot of the linear model and gives us a plot of the residuals in several contexts. So first you have the residuals plot versus the fitted values. So we know what residuals are. They're the difference between the observed value and the predicted value. And then this is the predicted value. Okay. And then we have the QQ residuals. This is a plot to check our outliers and also whether our residuals follow a normal distribution. Then we have here state location, which tells us also of the trend of your residuals. And we'll discuss this in a while. And then here, residuals versus leverage. If this has something to do with the influential data points and outliers and leverage data points. All right, actually there are 6, 6 all in all. We discussed last time that if we do this one by one, which is equal to, let's say, 1 first, it will give us the first one. Okay. The second one is the one that appears. Okay, the one, sorry. For this one class. Ito yung number 2. Yung QQ plot, which is equal to 2, that gives us the number 2 plot. Okay, number 3 is the scale location. Number 3, scale location. And number 4 is not the number, the fourth one here. Okay, the fourth one here is the Cook's distance. Yeah, so it identifies what observations could be influential data points. Okay, and it does not only have 4. If I make this 5, so dito yung kanina, yung number 4 kanina sa plot natin. This is the residuals versus leverage. And there's also a 6th one. Okay, 6th one. And this is the relationship between the Cook's distance and the leverage. This one. All right, so we'll take a look at most of this. Okay, and We also learned before that we can use the ggplot to create the same using the autoplot. The plot here seems to be better in appearance compared to the one above. Okay. All right. Let me pause for a while. Any questions so far? So I'm not really. I'm going fast there because we have discussed that in the past. Could you kindly chat, please, if you're able to follow along? Correction class nga pala. This is ggplot. Okay. How about the others class? Isa pa lang nag-reply. Okay. I hope the others will also respond, class. Okay. So 7 lang. Thank you, nevertheless. So let me once again copy this. Yung text class, i-copy ko na lang in the interest of time. Ordinarily, I would have discussed that and just allow you to take your own notes. Okay, so as I said, 6 different ways yung ano natin, ano yung diagnostic plots natin. Let's take a look at the first one, which is the residuals versus the uh, fitted. So if you run this code class, yung which is equal to 1 yun, ano? Yung first one. All right, so what can we see with the first plot for the diagnostics? So dito class, tatlo kagad makikita natin dito. Number 1, yung linearity ng data. Number 2, yung residual variance natin. And number 3, outliers. So just in this plot, we can already see 3 things. Number 1, is there a linear ba yung relationship ng data natin at saka ng ano ng 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 data natin, ng mga variables natin. In particular, yung independent at saka dependent natin. Okay, so it tells us some information about this. So if you take a look at the red line, kung medyo horizontal siya class, then you can see that this will tell us that linear yung data natin, no? Yung relationship nila. But dito mukhang nagbabago no? It's not really a horizontal line. We're not expecting, of course, a perfect horizontal line. Pero you can see here na medyo hindi talaga siya horizontal, may pababa, tapos may pataas. Okay? So this might tell us that medyo hindi horizontal yung relationship ng data natin. And also the red line also indicates yung homoscedasticity or heteroscedasticity ng data natin kung constant ba yung variance niya. If you as you can see class, yung ano dito yung plot ng residuals, it's fanning out, no? It's opening out. Ibig sabihin, while as the x-axis in this case, which is your fitted values, as the fitted values increases, the range of your residuals also increase. Pag lumalaking fitted values natin, lumalaki din yung ano natin, yung residuals. Okay, so it seems to be not constant. And then here you have some outliers that are observations that are outliers here. Okay, so as I said, yung first ano pa lang class, the first the residuals versus fitted plot. So what is that? As we mentioned a while ago, it's a scatter plot of residuals on the y-axis and fitted values on the x-axis. And what's the use of that? Detect nonlinearity, detect kung may unequal or non-constant yung error variances natin, and also outliers. And as I mentioned a while ago, kung yung red line natin kanina, horizontal line, it's indicative that there's a linear relationship, which is ideal. Yun yung gusto natin. Okay? So, kung well-behaved yung residuals natin, kung hindi siya heteroscedastic, dapat yung spread ng residuals natin random, no? And constant. Okay, how will that look, class? Dapat dito kunyari sa band na to, andun lang siya doon, no? To a certain band. Hindi siya nag-i-increase over time. Ito ang problem natin dito, class, kasi ano eh, hindi constant yung variance natin. Okay? Hindi siya up in a, it's not contained in a horizontal band, no? Kaya there seems to be our residual variance should seem to be heteroscedastic. Okay, and also walang mga outliers. Dito may possible na candidates for outliers. Okay? And you know, yung heteroscedasticity pwedeng ano yun eh. It could be a function of the non-linearity of the data and also the outliers. So, yung as going to discuss in a while, si heteroscedasticity pwedeng caused siya by the violation of the other assumptions. Okay, clear to, class, yung ano, yung sa residual versus fitted. Would you please chat if okay tayo so far? Clear ba yun yung first plot natin? Okay, thank you. Okay. All right. So some few more points here. Okay, I don't think I shared this with you. So share ko na lang din to. Okay. Okay, we can make use of another plot class. Okay, so from the car package, meron tayong CR. Okay? CR plot, yung component plus residual plot. Okay, and then let me just share this again. Share this. Control C. Okay, again, sorry, in the interest of time. Okay, so I decided to just put here some of the most important points as regards this one. All right, so again, yung plot 1 natin, yung residuals versus fitted natin, ito. No? It tells us about the linearity of the relationship between our variables, between our predictors and dependent variable. Okay, as we said, we can make use of this to test that visually, no? Visual inspection of a scatter plot. Okay, nonlinear patterns in the plot indicate violations of linearity, which is the case in our plot here. Natin mga residuals, iba paakyat na ganun, no? So had they been randomly formed, no? Random lang siya, tapos hindi siya nag-i-increase, hindi siya nag-decrease over the values of the fitted values. So yun sana ang maganda, ideal, homoscedastic. All right? So let's take a look at this. From the car package, there's this function, yung component and residual plots. So let's run this, CR plots, and then let's see. It will give us the relationship between, okay, your dependent variable and independent variable, which we have actually seen dun sa correlation plots natin. Nakita na natin dito eh. Okay, so ideally, okay, yung yung blue line na to, ito yung regression line, no? Okay? Ideally, sana andi dito yung natin, yung red line na to o yung pink line na to. As much as possible, dapat sumusunod siya dito sa sa dotted line na to. Pero mukhang hindi, no? And we knew this kasi when we computed for the correlation between education and the hourly wage, 0.4 siya eh, no? 0.4. So hindi siya ganun ka-strong yung correlation niya. It's moderately weak yung correlation, no? Eh yung tenure mas mababa pa, 0.32. So we might have issues here about linearity of the relationship between your independent variable and your dependent variable. For this one, makikita natin sa mga categorical variables sa factors natin, what we can see here, of course, are the outliers. So may mga outliers dito. Okay, so that's using the CR plots, no? As an addition to the what we discussed a while ago. So I don't think I have shared this with you. All right. So once again, paki-copy na lang to class as additional notes for you. All right. So kung relationship sana linear class, dapat yung ano natin, yung plot natin ng residuals natin dapat randomly dispersed, just like the one here. Dapat dapat horizontal line, but it doesn't seem to appear that way. Okay. All right. So also, as I mentioned a while ago, yung outliers or influential data points. All right. So I think we've had enough of the first plot where we're able to identify kung yung linearity ng relationship ng predictors natin at saka ng dependent variable, and also the presence of heteroscedasticity, if any, and then also the possible outliers. So sa plot 1 pa lang yun, marami na information. So let's go now to the third plot, which is the scale and location. So ito class, similar to plot 1 in the sense that it also gives us some information about whether the residual variance is heteroscedastic or homoscedastic. So let's plot this plot, which is equal to 3, so it will give us this one. Okay, ito. Yan yung scale location natin. Okay, and then I'm going to share this. Okay, sana okay, sana hindi masyadong mahaba. Okay, long. Too long daw. Okay. Dito, text ko na muna to. Share ko na ba yun? Anyway. Ayaw. Okay. And then let me just copy again the next one. The next batch para tuloy-tuloy yung discussion natin. Okay, let's discuss this class. Yung pangalawa, no? Which is plot number 3. Okay, as I said, if we run this, okay, scale location, and you're plotting the square root of the standardized residuals. What are standardized residuals, class? Yung residuals, convert natin into standard values. So residual E minus the mean of E divided by n minus 1, okay? And then square root of that, standardized residuals. Okay, so as you can see here, class, medyo no? The plot of the residuals, as we mentioned a while ago, similar to sa plot number 1, fanning out, no? Lumalaki over a larger fitted value. Okay, and then there are possible outliers here. Okay. Okay, and what's a test? Horizontal line with equally spread points is a good indication of homoscedasticity. But in this case, this is hardly horizontal, and then yung distribution ng ano niya lumalaki, di ba? So sabi natin hindi constant yung variance nito. Okay. This is a case in the model where heteroscedasticity seems apparent. Okay, we can, instead of just looking at it visually, there are tests class for, okay, naulit to, no? Sorry about this. Ulit, dapat sa baba ito. Alright, so first muna class, discuss natin, ano naman kung heteroscedastic yung residuals natin. What's the problem with that? Okay, so first we said that this is one of the assumptions dun sa Gauss-Markov theorem, okay, about OLS of ordinary least squares. Okay, sabi natin, if the assumptions of Gauss-Markov theory are met, then blue yung ano natin, no? Blue yung model natin, best linear unbiased estimator. Okay, now, pag hindi natin bina-violate yung homoscedasticity assumption, then our betas, yung parameters natin, are all unbiased. And also, yung standard, yung ano natin, yung variance natin, minimum siya. Okay? Ito I mentioned a while ago, among all unbiased linear estimators. Kasi pwede tayong pwede tayong mag-identify ng other linear estimators na unbiased, but there will only be one line of best fit. No? Kasi iisa lang yung may minimum variance. If we go here, class, okay, sandali ha. So ano mangyayari, class, kung hindi ma-meet tong assumption na to? Ibig sabihin, heteroscedastic yung residuals natin. Ang mangyayari, class, hindi magiging bias yung coefficients natin. Okay? O okay pa rin yung yung unbiased yung natin, yung coefficients, yung estimates natin. However, kung magkaroon ng heteroscedastic na residuals, class, ang mangyayari is that maapektuhan yung pag-compute ng variance covariance ng residuals, class. And when that happens, apektado yung standard errors natin. So pag apektado yung standard errors natin, apektado yung t-stat natin. Pag apektado yung t-stat natin, affected yung p-values natin. Okay? Therefore, medyo mali tayo kung mali yung p-values natin because of wrong t-stat, because of wrong standard errors, then tagilid yung natin, yung hypothesis testing natin, yung inference natin. It might not be possible at all, no? Pag heteroscedastic kasi yung residuals natin, class, okay, yung parameters natin unbiased, pero yung standard errors natin hindi na biased. Biased na. Okay? Biased na siya. Kung biased sa class, tuloy-tuloy na yan sa inference. Kasi affected yung t-stat, affected yung p-value, affected yung inference natin. Okay? Therefore, pag heteroscedastic yung residuals natin, yung estimates natin will no longer be efficient. Unbiased siya, pero hindi na siya efficient. Bakit siya hindi efficient? Because class, the variance now is no longer minimum. Okay? Hindi na minimum yung variance. Kailangan minimum yung variance, class, para maging efficient. Para maging blue. No? Alright, balikan natin yung model natin kanina and let's discuss what happens here. Okay, di ba ito yung natin? Ito yung summary mode natin. Okay, take a look at this. Alright, so kung heteroscedastic yung residuals, what happens to the estimate? Walang problema sa estimate. Unbiased pa rin yan. Okay? But what will now happen to the standard error? Okay, magkakaroon ng problem sa pag-compute ng variance, ng variance covariance natin for the standard error. So this becomes biased. Okay? So this becomes inefficient na to. Okay, so mali na to, class. Pag mali to, paano yung t-value? T-value is equal to the estimate divided by the standard error. Diba? Estimate divided by the standard error is the t-value. So if okay yung estimate natin, but the standard error is faulty, then t-value is faulty. If the t-value is faulty, then the p-value is faulty. If the p-value is faulty, then we might have wrong inferences. Okay, yung hypothesis testing natin magiging mali na, no? Okay, kasi for all we know, hindi pala significant to. Example lang. Okay? Especially kung masyadong malapit yung ano, no, yung p-value natin. It's quite close to 0.05. Okay, so that's what happens, class. That's the problem when you have heteroscedastic errors. Uh, yung variance natin nun. So pag ganyan, class, kailangan i-address yan. That has to be addressed. All right. Now, I shared with you here, this is a good reference, no? So could you kindly open this, Control C, and then i-download nyo to, class, kasi although this makes use of Stata, okay, but the theory behind is very good. Okay. So, okay, bukas, class, and tingnan lang natin sandali. Because I want you to download it and keep it as part of your reference. Basahin niyo siya, no? All right. So this is from the book of ito, no? From Berry and Feldman. Okay? And to a large extent, Allison and Pindick and Rubenfield sa econometrics, no? Okay. Yun ang ating reference. Allison, sinulat mo niya dito? I'm sorry, hindi yun nasulat. Okay, anyway. So it first identifies what heteroscedasticity is, di ba? Sabi natin, dapat yung variance ng error term should be constant, sigma squared, for all j. Constant siya. If the error terms do not have a constant variance, they're said to be heteroscedastic, no? Differing variance. Okay? Skedasis is dispersion or yung spread. Okay, so ito, ina-explain niya when scedasticity might occur. Ito, kanina, di ba? When an increase in the value, when errors may increase as the value of IV increases. Lumalaki yung IV, independent variable, lumalaki din yung ano, lumalaki din yung residuals. Okay? And it will look like this. No? As your independent variable increases, the residuals will also increase. Okay? And what happens is that pwedeng maging errors may also increase as the value of an IV become more extreme in either direction. Ito yon, no? Lumiliit na lumiliit yung IV natin or lumalaki na lumalaki, nag-i-increase yung ano, residuals natin. Yan. That's this one. This is an example of heteroscedasticity, class. Okay? So I leave you to read through this. Okay? And ito lang, no? I just want to point this out. Ano yung consequences ng heteroscedasticity? Okay? Sabi ko kanina, si heteroscedastic class, pwedeng resulta yan ng other violations. Kung na-violate yung linearity, it could affect the residual variance. Okay? Tapos, ito, here, class. OLS estimates are no longer blue. Hindi na best linear unbiased estimator. Okay, the parameters, yung efficiency natin, unbiased pa rin. Okay? Pero yung ano natin, since yung standard error natin hindi na siya accurate, then affected na yung up to the last yung inference natin. Kaya hindi na siya blue, no? Okay? Among all the unbiased estimators, OLS does not provide the estimate with the smallest variance. Yan. Kasi yung variance niya hindi na yung smallest. Kaya hindi na siya efficient. Okay? All right. So again, I leave you, class, to go through this. Ito, class, example ng ano to, no? This is an example of homoscedastic residual variance. Ito yon, randomly distributed across this band. All right, and then there are tests. Titingnan natin to. Si Bruce Pagan test. Okay, there are other tests. Si White's general test. Si Gold quant test. Okay, we'll just take a look at two. All right. So how to deal with that, class? Ito. Basahin nyo rin to, no? pwede nating baguhin transform natin yung variables natin. Okay, sometimes, yung heteroscedastic results from the improper model specification. Okay, so there may be subgroup differences. Effects of variables may not be linear. Perhaps some important variables have been left out. So yung specification bias. Baka may kulang. No? Baka instead of education, dapat kasama si education squared. Okay? Kung may problem sa ganito, class, kung may problem sa model selection natin, ayusin muna yon. Okay? Kasi isang remedy, we're going to study the remedies, no? Isang remedy sa heteroscedastic residual variance is what we call the weighted least squares, WLC, and also the use of robust standard errors. Ito, aaralin natin to, class, no? Yung weighted least squares at saka yung robust standard errors. All right, so let me leave that, class, and balik na tayo dito, no? I just provided you with a very good, of course, class, this article will not come to you, no? Ikaw dapat ang lumapit dyan at aralin nyo. Hindi yan tutulong sa inyo sa case nyo without you reading it. You have to read it. All right. So first, class, we can make use of the NCV test, non-constant variance test. So isulat nyo tong na to. From the car package NCV test, ang null hypothesis dito is the residual variance is constant or homoscedastic. Okay? So pakirun, class, yung code chunk na to and tell me, based on the test, 1, homoscedastic, 2, kung heteroscedastic. Okay, I'll wait for your response. Run this code chunk and tell me if based on this statistical test, kung homoscedastic or heteroscedastic yung residuals natin. Okay, answer please. I hope everybody will answer. 1 kung homoscedastic, 2 kung hetero. Sir? Okay, we have one answer. How about the others? Waiting for the others to key in their answers. 1 or 2? Good. Then coming, class. What result does the non-constant variance test give us from the car package? Okay, some more please. Ano, makaabot tayo ng 50% responses. Low class, only 4. It's a pretty bad rate. 5 out of 20. 25% lang. Come on, class, come on. How about the others? 20 plus tayo dito. Anong result ng test na to, class? NCV test. My 2, yeah, 2, 2. Okay. So the answer, class, is you're correct, no? It's heteroscedastic. So the visualization was ang tawag doon? Validated by this test. Okay? Yan. The p-value is less than 0.05, way less than 0.05. So we reject the null hypothesis that the residual variance is constant or homoscedastic. Okay? So based on the non-constant variance test, heteroscedastic na yung variable natin, yung residuals natin. And let's also have this one, about this one. Ito naman yung Bruce-Pagan test. What does the Bruce-Pagan test tell us about the residuals? Same din yung null hypothesis niya, no? Residual variance is constant. Okay, once again, class, 1 or 2? And this is from the LM test, no, linear model test package. But this is not from the car package. This is from the LM test package, linear model test. This is a powerful package, class. Okay, so what do you have, class? Okay, let me answer that. So ganun din, class, no? P-value is way below 0.05, so we also reject the null hypothesis that the residuals are homoscedastic. So whether we use the NCV test or the BP test, using the Bruce-Pagan test, yung Bruce-Pagan test, very popular to, no? Okay, this is one of the widely used test. So ang ginagawa dito, rene-regress din, class, no? What we regress is kukunin yung residuals and then square siya and then i-regress dun sa original yung sa model ng education, experience, civil status, and etc. I-regress dun. Tapos hahanapin kung may yes, Carlos, what's your question? Paki-share sa lahat yung question mo, please.
Sir, are we gonna use something like this for our model diagnostics?
Oh, nagda-diagnose tayo ng model natin. Ba? We're testing the residuals here. We're now into model diagnostics. Ito na, class, yung model diagnostics. Since kanina pa, yung ano natin, yung unang-una, tinest natin yung plot 1, tinignan natin. We gave some comments about it, about our residuals, about the linearity of the data. And then yung plot 2, ito, di ba? Yung plot 3 actually. Scale location. Ito na, class. Ano na to? Model diagnostics na to. Okay? So in case you're still confused kung asa na tayo, nasa model diagnostics tayo. Okay. Then we're looking at statistical tests for homoscedasticity, no? So ito, NCV test, BP test. Sa BP test, as I was saying, class, gumagawa ng model na to, gumagawa ng linear model. So ano yung linear model dito? Residual squared, okay? Diniregress dun sa ano natin, sa independent variables, yung 4. Okay? Tapos hahanapan ng titingnan yung ANOVA and then chi-square test para malaman kung may significant relationship ba siya. Okay? So it turns out that there's a significant relationship. Well, as far as the chi-square test is concerned, no. Pero based on our null hypothesis here, okay, ang p-value is way lower than 0.05. Therefore, class, ito, reject natin to. Okay? All right, there's another one, class, White's test. So similar to ano to. So I'll share also the code kasi we're not going to really discuss the code now kasi it will involve the discussion of interaction. Okay? Okay? Ano na muna, class, no? I-hold muna natin itong discussion ng interaction. That's the I there, class. So ito, may regression din. Alright? So ano nangyari dito? Mod, yung original model natin, and then may dinadagdag pa tayo, no? Ang sinasabi dito, dagdagan natin ng predictors. So idadagdag natin sa model natin yung predicted values at saka predicted values squared. Okay, take note, no? Pag sa independent variable class, nagkakaroon ka ng transformation, kunyari ini-square mo, you will have to put here I. Okay? So i-discuss ko to when we go to interaction. All right. So if we run this class, ganun din yung null nito, no? Hypothesis, ganun din. If I run this, so ganun din, no? Same as the Bruce-Pagan test. Okay, both reject the hypothesis, the notion that the residuals are homoscedastic. All right, and then there's this other one, class. Ito type nyo nga to. At the same time. Okay, there's this other test, no? From the performance package, performance, and then check heteroscedasticity mod. Okay, if we run that, it will tell us, warning, heteroscedasticity non-constant error variance detected. P-value is less than 0.001. I guess this also uses Bruce-Pagan. Kasi output niya, hindi niya binibigay yung Bruce-Pagan statistic, binibigay lang niya yung yung inference. Okay, so ito yung test natin for what we did was to take a look at heteroscedasticity from a visual perspective and also from a statistical perspective. So powerful yun. And we also studied, so what kung heteroscedastic yung residual natin, yung variance natin? Maraming implication yun. Pag heteroscedastic, then hindi na blue yung ano natin. The coefficients are still unbiased, okay pa rin siya. Pero yung inference natin, paano yun? Kasi mali na yung standard errors, mali na yung t-values, mali na yung p-value. So carried forward na yun, up to the inference. So we cannot rely on our inference kung significant ba o not significant. So hindi natin masasagot talaga yung null hypothesis natin. Okay, so you see the gravity class of okay, i-share ko na lang ito sa inyo para mabilis tayo. Okay, I have a few more minutes. Isasabay ko lang dun sa kabilang section, no? And I'm going to share also the recording from the other section kasi mas nauna sila. Umabot kami sa normality na residuals eh. At least dito makapagsimula tayo, class. All right. So, again, ang dinidiscuss natin, paano kung yung residuals natin naman hindi normally distributed. So we use the normal QQ plot, which is second plot. Run natin to. Okay. So dapat class yung plot natin, dapat yung along the QQ quantile plot, dapat yung residuals natin dapat close to this. Ito kitang-kita na kagad, na may problema tayo sa normality. And we have also outliers here. Okay, we have problems with normality as far as the higher quantiles are concerned. All right. Again, so what, class? So what kung hindi normally distributed? In fact, sabi nga natin, 'di ba? Hindi naman talaga kasama sa sa assumptions ng classical linear regression model. Okay? So, let's read what I shared with you. Okay. A violation of the assumption of normality of residuals may result in incorrect inferences in small samples. Okay, kasi class, pag hindi rin kasi yung computation of p-values is also based on normality of residuals. So, again, affected din yung pag hindi normally distributed yung residuals, affected yung standard error. So, alam natin, affected si t-stat, affected si p-values. Okay? So, p-values rely on normality assumption. So kung hindi siya valid, then inaccurate yung inaccurate yung inference natin. Okay? Also, our confidence intervals will be probably wrong. However, in large samples, okay? So may mga journals, may mga articles na nagsasabi nito, At least 10 observations per predictor. So if you have 10 predictors times 10, so dapat 100 observations, at least 100 observations yung data mo. Kung konti lang data, it's possible that normality, violation of normality is critical. Pero kung malaking data natin, walang problema. Okay? Although rule of thumb lang to, Okay, let's go to this. Itong article ni Smith and Finan. Okay, I share this with you. Paki-copy class and basahin natin some portions here. Control C. Okay, you can cite this as an article. Okay. All right. So what does this say? It's almost time, class. If you need to go, okay, you may do so. I'll just continue this for recording purposes. All right. Itong abstract na to, so this is a journal article, Linear Regression and the Normality Assumption. Okay. So ang sinasabi dito, may mga research na kapag hindi normal, ang ginagawa nun, one way to address that is to transform your data. So pwedeng yung dependent variable mo gawin mong log o gawin mong square, etc. No? Pero ang sinasabi ng article na to, that might not be needed, no? Kasi okay, so ang context nito, no, sa medical field yung research na to. Sa medical field kasi very important yung inference. Kasi kunyari kung medicine ang pinag-uusapan, kung effective ba yung medicine or not. Eh di pag mali yung inference mo, then makaka-affect yung yung conclusion nyo doon based on the efficacy of the medicine, di ba? So sa atin hindi masyado sa econometrics. Kasi ang mga pinag-uusapan naman natin mga economic, financial or econometric variables, hindi masyado yung pag medyo nagkamali sa inference based on error dun sa violation of normality. Okay? Ang gusto ko lang sabihin dito, class, for some data, baka hindi na kailangan i-transform yung let's say yung dependent variable kasi doing so will bias your estimates, which will not happen if the residuals are not normal. So yung pagiging biased point estimates, nangyayari lang yan kung possibly i-transform mo yung data, baguhin, kunyari gawin mo log. Okay? It will not happen if you use the same data and then naging yung residuals mo hindi normal. Okay? So ito din sinabi dito, no? Assumptions on the parametric model, absence of, okay, diyan, ito. Conclusion na lang, class. Okay. So given that modern ito healthcare kasi so importante sa kanila talaga to, no? Focusing on the normality assumption is often unnecessary. Okay? So among all the violations, ito yung pinaka sabihin natin ito yung pinaka quote unquote weak, no? Hindi masyadong critical. All right? So there are way to test this. So i-share ko na lang sa inyo to. Okay? Now, Control C. Control V. All right, so here are tests for normality. So if we test this using Shapiro-Wilk, okay, ito. So p-value is very low. Again, the null hypothesis is that normally distributed yung residuals. So reject din natin to, no? Okay, hindi normally distributed yung residuals natin. Also this one, class. Okay, Kolmogorov-Smirnov test. Ganun din, no? So I think I shared with you the code. Okay, ganun din siya, no? P-value is less than 0.05. Okay, and lastly this one, before we call it a day. Control C, Control V. So last, okay. So there's a good statistical test also from OLSRR. Itong OLS test normality. So OLSRR is not only used for stepwise regression, pati yung test ng ng linear model natin. So if we run this class, magbibigay siya ng apat na test. Shapiro, yung kanina sa taas. Ito din, Kolmogorov, Smirnov, Kramer at saka Anderson. Binigay yung statistic and p-value. Lahat to, class, ang test niya, null hypothesis is that the residuals are normally distributed and all of them reject that one. Okay? So ito, yung plot lang to kanina, pareho din yung QQ plot natin, and ito histogram lang. Histogram. Okay, and you can see here that our residuals, they're really not normally distributed. Medyo peak siya dito, no? Mataas ang peakness niya. Okay, and then meron siyang tails dito. All right, so let me stop recording now.